Good evening and welcome everybody to N Simplex Pachinko. This is Obi-Wan Pez. How are we doing on stream elements? Is that doubling it or anything like that? That was weird. Oh no, I see what happened. Thank you for the follow. I'm just not quite making it today. Okay. We're doing okay. I promise. Alright. Well, I hope everybody's having a good week so far. Going a bit crazy over here with the I don't know, not sleeping or something. Alright. Unless I am very much mistaken, this is going to be another branch here. The whole point at this exact moment in time is that I'm not using a calculator, so that can always be fun. So, this Collatz branching is also something that I'm going to have my students do in my pre-calc class on Friday, and they have no idea that this is what's going to happen. I'm going to ask each of them to pick a random number that they think that no one else in the room is going to pick, between 100 and 1,000, so just a random 3-digit number that they don't think anybody else is going to pick. And then they're going to follow the same rules for the Collatz conjecture. Of course, I'm not going to tell them any of this, just that if really, right, fine. Where'd it go? Oh, I'm going backwards. That's why. Hey, yo. So for all a sub n plus 1 is going to be a sub n over 2 if a sub n is even, and 3 a sub n plus 1 if a sub n is odd. So they'll be told to take their random 3-digit number that they have and follow this particular procedure until eventually everybody's going to get back to 1, and then when they again hopefully realize what's going on, they're going to get to 1, which cycles back to 4, which cycles back to 2 to 1, which cycles back to 4, then 2 to 1, then 4, then 2 to 1. And eventually what I'm going to do is have them, write it out as a sequence first, and then second, take their particular branch that they created and write it on whatever probably it might be a window. I can't decide. It's either going to be a window or a board space. So board space might just be easier. So we're going to be dealing with this. They're going to individually create their own sequences. So for instance, the sequence starting with 227 would be 227, 682, 341, 1024, 512, 256, 128, 64, 32, 16, 8, 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1, etc. And like I said, I'm going to try to get them to, essentially what's going to happen is they're going to draw a tree wherever it is that I'm going to have this done. And hopefully all of them will just be like, what? Alright, so Blainland, I got your problem pulled up. Okay, so consider a particle moving along a path in the shape of an ellipse given by the equation. Nope. Already messed it up. Parentheses x plus, nope. X minus 1 squared divided by 4 plus 4y squared equals 1. Yeah, that's a really small, it's a really semi-minor axis. Alright, so alright. So the semi-major axis is 2. So that's the square root of the 4 that's in the denominator. So we're somewhere about here. Give or take, right? And this vertical distance is going to be 1/4, nope, 1/2. Yep. here's going to be 1. It's supposed to be 2, that's supposed to be 3, and then this is supposed to be -1 here. Okay, find a parametric equation. We'll model a particle moving on the top half of this ellipse such that at t equals 0 it's located at 1, 0. So this is going to be 0, comma, -1, 0. All coordinates will be listed as t, x, y. Okay, and it's located at t equals 1. It's going to be at 1, 0.5. 1, 1.5. So yeah, we're moving this way. Looks good. Alright, so to parameterize this thing in terms of t, so you can okay, so I have recreated accidentally the shell of this particular thing. Accidentally. I suspected I knew what it was. It's just that I ended up creating something a little bit different than what I meant. It's cool, whatever. Okay. So, yeah, I got your solution. Hang on. Oh no, part B. I see. Okay, we'll come back in a minute. So here, what we've got is our semi-major axis is a distance of 2, and it's starting at its lowest value. So the furthest negative x direction. So I would suggest that your x of t is going to be equal to asterisk, right? this is going to be a rough sketch. It's not going to be 100% correct yet. So the first iteration of this, I would say, okay, we want this to be the largest negative value, so we want x to be the cosine. And we want it to be a negative cosine so that it starts at the lowest value, -1. Then we want this in 1 second to do a quarter of the ellipse. And since it's symmetric around all those 4 sections, the whole period should take 4 seconds. So period is equal to 4 seconds, which is going to be equal to 2 pi over b. Alright, and then naturally b could be equal to 2 pi over the period, tau, which is 4. So that means that b is going to be pi over 2 times t. Alright, then our a value out front needs to be the semi-major axis. So how far away are we going eventually? And the answer there is 2. So we need this to be a -2, not just a negative. Almost completely forgot about that. So blame that I'm doing this without looking at the answer you provided yet. But so we want this to go 1 second, to go from here, 0, -1, 0, up to 1, 1.5. Right? So this is a quarter of the ellipse. And the ellipse is symmetric among all 4 of its quadrants. So it means the whole period is going to be 4 seconds. So the whole period being 4 seconds, we then say, okay, that's going to get us a b value of pi over 2. Well, no, you gave a time. You said it goes from t equals 0 to t equals 1. Yep. So your b value is the frequency at which this particular trig function works. You could also let it be abstract, that's fine. But this one's going to get you the right amount of time. All right, so then we want our y's to be represented by the sine value. Semi-major or semi-minor is going to be a half. So it's going to be a 1/2 sine of pi over 2t. And this is actually important, that our pi over 2 needs to be the same. Because again, it takes 4 seconds to make the complete loop. Otherwise, if you don't, you get really cool stuff. Let me see if I can... I don't have anything up right now that is particularly bad. That's yours. Desmos? Really? That's not useful. No, I mean, so every time that I have brute force something, I have eventually realized that that is an opportunity for me to learn something new. That there is a method. It's just that I don't know it yet. So in this particular case, it's not insane or inappropriate. It's just that there's a more efficient way to do it, so you don't have to brute force everything. So where you use a sledgehammer, I use lockpicks. Yeah, and that could work too. There we go. Yep. Oh, I see. Yeah. Well, that also works in this particular case. You just got to be careful. Um, just got to be careful you're not messing something up. All right, so let's go like this. I just plugged in two kind of random values to make this work. Okay, so this was going to be a -2 cosine pi over 2t, comma, 0.5 sine pi over 2t. Okay, that centers everything. And then we say that the x value is going to be shifted to the right one, so we can add 1 to the outside of this thing, which then moves everything just over one space. Right, we go from 0 to, let's just show, well, we're going on to, all right, 0 to 1 is 1 second. So really what you've got, Blainland, is you've got this going from like -2 cosine theta and 1/2 sine theta, with theta going from 0 to pi over 2. The parameterization that I'm using here is intentionally using t, our time amount, as the thing we really care about. How are we doing there? Okay. So the +1 comes about because we just want our x values to be shifted to the right. We want our semi-major axis, or we want our center to be focused around 1, 0. So our x value is just going to have to be 1 bigger in order to force everything to move that way. It is kind of counterintuitive given how much I've been focusing and stressing on making sure everybody understands function transformation. And in function transformation, if you're going the x direction, you subtract, right, on the inside of the function. But that doesn't really work here anymore. If we subtract on the inside of this particular cosine function, that's just going to shift where we start around the same ellipse. But the good news is not like too complicated. Okay. So here the outside of the function is actually where the x is rather than where the t is in terms of parameterization. Well, I said not that complicated. There's far more complicated things that we could be doing. So for instance, this would be much more fun. I know. It will if you get there. Just so in this particular case, we actually have something that's going back and forth here. This is going bouncing off of each of these portions and then going back and forth like this. I set t to be 15 just so that we could kind of see what was going on here. So this is a much more fun equation. So if we let the period of the cosine function be 2 pi, but the period of the sine function only be 4 in this particular case, this is what we get. So we've got this path which starts at -1, 0. Can you actually see my cursor? I don't even know. No, I'm not even on the right thing. There we go. So you notice up here, we've got our -2 cosine of t plus 1 and 0.5 sine of pi over 2 times t. So now our periods don't match each other. If I put this as just pi, what's happening here is that this is bouncing along this parabolic trajectory, and every time it reaches the endpoint over here at 3, -0.5 and 3, 0.5, it's just bouncing back and forth like this. If I take away the pi and just make it 1, then this now becomes something that gets ever so slightly off every time it goes near where it would have been on like the next period. So here, our -1, 0 comes up, goes up to approximately 0.5, 0.5, comes back down here to now really close to 3, -0.5. Doesn't actually hit it. Kind of goes along this curve and comes back. Goes all the way around here, down this way to like -1, -0.2. And then back down here to 0.5, -0.5, -0.5-ish. And then goes up here, reaches a curve as it comes close to x equals 3, and then swings back again, and then back again. This is where it stops at t equals 15. Okay. I got you. So, with our pi over 2 for both of these, now this allows this perfect elliptical trajectory. Okay. So part B then said, at what speed is the particle moving when it reaches the y-axis at 0, √3/4? Okay. So at what speed is the particle moving? This has to take into account both its x velocity and its y velocity. So I want to say that that's going to be like find the magnitude without necessarily knowing what I'm doing here. Right? I think that what it's going to be is the gradient at that particular point. This is 0, comma, root 3 over 4. So I think we want to find the gradient. Oh, I'm not on the thing. So yeah, right here, at this particular point, I think we want the gradient of the function we want the parameterized directional derivative. Yeah. Okay. So, where's my book? Well, I mean, it should be. So 394. See if this matches up with what you saw. Okay. So I've got, instead of worrying about derivative or gradient, our velocity vector v. So I was right that we need to take the absolute value, which is going to be equal to r prime, which is equal to the square root of r prime dotted r prime. Which is dSdt. Man. Hey, 3 left seconds. Okay, so what I'm seeing here is if we had a function f, then we'd be looking at taking the gradient, so the directional derivative, in order to just say, well, the rate of change of x, y, and z in terms of t is going to be, whatever it's going to be. When I asked you about cubic feet, yeah. So since we don't have like a definite function for this thing, square feet, not cubic, yeah. That happens. No, that's not good. Okay. So R R is a parameterized vector. Okay. So R of t is going to be equal to this thing, -2 cosine of pi over 2 t plus 1 parentheses I hat plus 1/2 sine of pi over 2 t j hat. So if you're looking at square footage, then you want to calculate the area of whatever space you're looking at. So if it is a rectangular space, that is going to be the easiest thing to do. That's going to be length times width. If it is a non-rectangular space, you can either break it up into right triangles or rectangles. And then it kind of depends on what you got. Okay, so Blainland. Yeah, it doesn't quite work that way. Alright, so Blainland, then what we've got here is if R of t is going to be this thing, R prime of t is going to be the derivative of each of these things with respect to t. So here, this is going to be a -2. Derivative of cosine is a negative sign, so this is going to be a +2 sine. By the chain rule, pi over 2 comes out, knocks out the 2, so we just get pi. So this is going to be pi sine, pi over 2t. The 1 is going to get eaten up. This is I hat. Plus. Same thing over here, only this time it's going to be pi over 4 times the cosine of pi over 2t. J hat. Okay, so that's R prime. Then we're going to dot R prime with R prime. Oh man. Let me just just double check, make sure I'm doing this right in my head. Okay, if that is R prime, then dotting Whoa. And there we go. Okay, so Sorcerer1, thank you very much for the follow. And Mr. I Love Barbecue Chicken, thank you very much for the follow. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We are here doing some math tonight. And if anybody has any questions, feel free to drop them in the chat. We'll get to it as soon as we can get in there. So, the way that we had it, right? If you just put the sine of theta and the cosine of theta into the equation, that works pretty well, and it gets you the same ellipse. But then it doesn't actually get you like a time to go around the ellipse. So that's when I altered the b value that's sitting in front of our t. So the constant multiplier inside the function. All right, seriously. Oh. Yeah, it's just scalar multiplication. All right, so r prime dot r prime is going to be pi sine pi over 2 t. It's going to be squared plus, all right, pi over 4 squared cosine squared of pi over 2 t. All right, and then it's square rooted that result. Well, that makes it interesting. So if we let this be 4 pi squared over 4 sine squared of pi over 2t plus pi squared over, it's over 16. Man. Alright, we'll go back. This is not 4 and 4, it's going to be 16 and 16. cosine squared of pi over 2t. Okay, so I'm going to take one of these, which means that we're leaving behind 15 pi squared over 16 sine squared of pi over 2t. Okay, plus 1 pi squared over 16 taken from both the sine squared and the cosine squared. Means that all this stuff is going to be 1. So we're going to get here a 15 pi squared over 16 sine squared of pi over 2t plus 1 times pi squared over 16. That's r prime dot r prime. And then our velocity vector, the speed of that velocity vector, is going to be the square root of this stuff. Which we can take a pi squared over 16 from each. This is going to be a pi over 4 multiplied by the square root of 15 sine squared of pi over 2t plus 1. Alright, Blainland. That's what I got. How to calculate probability. So, mostly. Which kind of probability you're looking for today? Okay, so for any probability that you want to talk about, the most basic stuff to do probability of some event occurring is going to be equal to the number of successes divided by the total number of outcomes. So if you have a standard 52 card deck, which comes with 2 jokers, right, this is going to be 54 cards in total. So if you're just saying, like, shuffle up and deal 1 card off the top of the deck, the chance of you getting a joker on that first card is going to be 1 in 50, or no, sorry, 2 in 54. Nope. Ace through king, which is 13 cards of all 4 suits. So hearts, diamonds, clubs, and spades. So 13 cards in each suit times the 4 suits that we have gets us 52 possible combinations. And so we have 52 cards, and then we have the 2 jokers on top of that. Yep. So the probability of drawing a joker in 1 is going to be 2 in 54 or 1 in 27. So, Mr. I Love Barbecue Chicken, if you have a, let's see, MSE, what were the other ones? Oh, Stack Exchange, gotcha. Yep, it's there. Okay, cool. Yep, I'll take a look at it. So 3 left seconds we got. I would say that this is probably one of the more annoying ones that you might see in a standard like probability and statistics kind of class. So what's the probability of you getting a joker in a hand of 2? And let's just do 1 joker. There's a reason. So if I say, what's the probability of receiving 1 joker in a hand of 2 cards? Then what we have is, we know that we have 2 cards that are going to be in the hand that we draw. So what we want is that there's going to be exactly 1 joker and exactly 1 other card. So on the first card, the probability of choosing a joker for this first card is going to be the same as it was up above, just 1 in 27 or 2 in 54. And then over here, the probability of receiving any other card that is not a joker specifically is going to be 52 over the remaining 53 cards. So again, if we end up getting the other joker, technically it's a loss, because we said we only want, what's the probability of getting one joker in a hand of 2? Alright, and since we want both of these things to happen at the same time, we're going to multiply their probabilities. So we are allowed to multiply what are called independent probabilities. So two things that cannot affect each other. So for instance, when you draw 2 cards from a deck of cards, the draw of one cannot affect the draw of a second card, except in the fact that the number of successes, or in this case the total number of cards remaining, is going to change. But like, the act of drawing a 2 of hearts does not cause something else to happen with the next draw. Right? We're not any more likely to get the 3 of hearts now that we've drawn the 2 of hearts. It's considered 2 independent events, with the exception of, again, the total number of available cards is going to tick down every time you draw a card. Or we might say one event's outcome doesn't affect the probability of other events' outcomes differently. So, stuff like that. So here we can multiply these two things together. We end up getting 2 times 52 divided by 54 times 53, or 1 times 52 over 27 times 53. So 52 over 27 by 53. Which is going to be I'm okay, I promise. 1021 plus 350 and 60. 410. So 1431. And actually, those can be simplified further. 52. Oh no! Raiding party! No, I can't. Never mind. Oh no! It's a Vainglorious raid. Welcome to the math party, everybody. Oh no. What have you gotten your viewers into? Good evening and welcome, everybody. This is Obi-Wan Pez for and Simplix Pachinko. This is our home for all things mathy on Tuesday nights. So we're doing some probability and statistics at the moment. We're doing some vector calculus in the background. Parameterized paths around an ellipse. Oh, it's fun times. What were you all doing tonight? Ah. All right, so anybody who does not know Brandon, he runs this channel, Vainglorious Gaming, and loves to do city skylines and Astroneer and a bunch of other cool stuff. Hoo-hoo. Tsunami and tornado at the same time. Very nice. I hope you didn't destroy too many people's lives in the process, but yeah. So if anybody has not seen Brandon in action, go ahead and check him out at Vainglorious Gaming. Got an awesome channel, got an awesome community. So welcome in everybody, and go do whatever you need to do. Hang out, lurk, ask math questions if you have any. They have this weird thing against card counting. There's no law. Also, no law of them picking you up by the belt and throwing you out the door, but, you know. Yep. So, 3 left seconds. This one does actually get kind of annoying. So I will highlight it, but I don't think you're going to see something like this too often. This gets really complicated because now you have, like, possibilities. If you have a hand of 2 cards, and I'm super simplifying this, again, we're going to multiply our probabilities together. The possibility of the first card being a joker is going to be, again, 2 out of 54. The probability of the second card then also being a joker is going to be 1 out of the remaining 53. Okay. Then we also have another possibility, is that the first one was a joker, and the second one was not. So the second one not being a joker is going to get us this 52 out of 53 again. So just like we had during the last one. Now here's where the things get a little bit weird. Because these are independent events and these two things cannot possibly happen at the same time, what we want is that either of these are successes, either the top one or the bottom one. And when you have two things that are mutually exclusive from each other and their probabilities are going to describe separate events, but both of them still count toward our, like, successes, this is going to be added. So we can take 2 out of 54 by 1 out of 53 plus 2 out of 54 by 52 out of 53. Find their individual probabilities and then add them up. Now there's also something else going on here. It didn't actually matter in which order I get those cards. So it could have been that our jokers could have been the other way around. or our other joker and the other card. Could have been the other way around. So here we have two possible ways in which we could get each of these things. So this is going to make both of their individual probabilities get multiplied by 2 as well. So like I said, this is where it gets a little weird. So here, if we get 2 out of 54 by 1 out of 53, plus 2 out of 54 by 52 out of 53, parentheses, and then we multiply all of this by 2, the total probability of getting at least one joker in a hand of 2 cards is going to be 2 out of 27. So this also gets into a different one. This number right here, 2, isn't just 2, just by itself. We could describe this also, and this also generalizes to, like, if we had a hand of 10 cards, then we wanted at least one joker. So, like, how would we do that? Well, there's a lot of different ways that we could rearrange those cards and still have the same hand. And so we don't care about those particular things. Unless I just did this wrong. Right, because for both jokers, we need both of them in order to count as a success. I mean, technically, if the jokers themselves are not necessarily identical, so I know in a lot of my cards, like, one of the jokers is slightly different from the other. You know, technically, having it one way and then the other is the same thing. And I don't think we need to multiply by 2. We need to divide by 2, don't we? Oh dear. This is one of the reasons why I did not particularly like teaching this particular class. I just need to do it more, really, is the problem. Alright, so this number 2 really comes from this idea here, which is that of 2 that we have, we're going to choose one of them. Yeah, now I'm definitely messed up. Cool, cool, cool. I always hated this stuff. I mean, it's cool, but at the same time, it's like I always had problems with trying to remember how to where to put the choose stuff, even while I was teaching it. Okay, so let's go about it a different way then, because this will help us figure it out. Arg. Well, it's not 1 choose 2 anyway, it's 2 choose 1. Jeez. Alright, so like, one of the ways that we can do this is say that the total number of cards that we can select is going to be 54 for the first one and 53 for the second one. Right? Now, assuming that, again, all of the cards are unique, so even the jokers themselves are slightly different from each other, so we can tell them apart. Alright, then the top is going to be the number of ways that we can choose Yeah, okay. So in this way, since we're choosing both jokers, then we have 2 jokers, and we have to choose both of them. So it's 2, choose 2. Okay, so then that makes this 1 over 54 by 53. So it's kind of a long shot. This would be 2862. So you have a 1 in 2,862 chance of selecting both jokers. Meanwhile, up top here, this is another way to do it. Okay, so let's get rid of this thing, because this is probably going to be wrong now. Maybe not. All right, plus, this is going to be, again, 54 by 53, which is going to be 2862 on the bottom. Then up top, this is going to be, of the 2 jokers that we have, we need to choose one of them. And also, of the 53 remaining cards, we could choose any of the 52 that remain. No. Okay, so I was calculating 1431 was from 27 by 53, which then if we increase 27 by a factor of 2, we get 54 by 53, which is 2862. you count arrangements at one place, you should be doing it at both. Oh, in the bottom. I see. Of 54, choose 2. Okay, that's 1. Of 54, choose 2 is going to be 54 factorial divided by 2 factorial 52 factorial. So that's 54, 53 over 2, which is then going to be the same as what it was up there. Yeah, okay, I got you now. 1431. Okay. So 2 choose 1 is going to be 2 times here 53 choose 52 should be 52. But, you know, just make sure. Yep, 53. But I said 52. All right, well. 2 by 53 divided by 1431. So that 53 is going to get taken out from both. Here that leaves 27. So 2 out of 27. Then it's going to be the sum of those two things. So 1 over 1431 plus 2 over 27. 1431 is 27 by 53, so this is going to be 53 by 1 plus twice 53 over 1431. So this is going to be 106, 107. Okay. Yes, thank you for that. All right, so 3 left seconds. Very sorry, that's probably way more than you wanted to know. Alright, so Blainland, a 4.26 kilogram block is going up a 33-degree ramp. Keeping in mind it's been a while since my last physics class. 33-degree incline at 7.81 meters per second. It's going to lose 34.6 joules in friction. 4.26 kilos. I don't really like free body diagrams, but we got gravity. So force due to gravity is going to be mg in the direction, well, straight down. Normal force is going to be applied perpendicular to the incline. So if that angle is 33, this angle is 33 here. This is 33. This is a right angle. That could be a right angle. $57. Yep, all right, and this is also a right angle. So these are also 57. And 33. Okay. Figure out how to make that work later. All right, let's assume that this is going to work this way. So the initial kinetic energy plus potential energy is going to be equal to the final kinetic energy plus potential energy plus heat due to friction. So we already know that there's a loss of 36 and 34. 34.6 joules. And then here we got our potential energy. The potential energy is going to be what we don't know. So we want to know how far is this going to go? How high is it going to go? We should be able to figure out what our mgh is going to be for this particular thing. Mass and gravity don't change. Height is going to change. Plus 1/2 mv squared. V is going to be 0 because it said how far is this going to slide. And if this is going to have some friction as it's heading up an incline, it's going to eventually stop. So with this eventually stopping, we can say that at that moment the kinetic energy is going to be 0 and it's all potential and heat loss. Alright, so then potential energy is mgh1. In this case, h, we're at the bottom of the ramp. H is 0. So all of our potential energy is gone. Or there is no potential energy. It's resting on the ground. And then it's being shoved up this ramp. Plus 1/2 mv squared. Okay. So the velocity is also in the direction of the ramp, not in the direction of height. So that's going to be slightly different. Interesting. So 1/2 times 4.26 kilograms times v squared is going to be equal to mass 4.26 kilograms times gravity so 4.26 kilograms times 9.8 meters per second squared times height 2. Now we're going to subtract over negative 34.6. We want to solve for h2. So h2 is equal to, this is going to be 2.13 v squared minus 34.6 all divided by this product here. Can't do that one in my head. So 4.26 times 9.8 is going to be 41.748. Alright, so what about that velocity? So the initial velocity is 7.81 meters per second, but it's in the direction of the incline, and height is vertical. So our velocity vector so this is our 33 degrees. We want to know what the velocity in the height direction is going to be for this, because that's the part. No, that's fine, because it's yes. Okay. The horizontal component is adding to the friction, but it's already accounted for. So we've lost heat due to friction, or we've lost energy due to friction. So that's here. That's already been accounted for. Okay. So v squared is going to be, again, the thing that is in the same direction as the height. So up and down stuff. So this is going to be v sub h. So the sine 33 degrees is going to be equal to so v sub h over 7.81 is the direct line distance. I mean, in theory, we have to account for the fact that this is a 33-degree slope. Because if it's like an 89-degree slope, it's practically going nowhere, right? All of that energy has to be taken into lifting this thing up. Could be wrong, and this could already be accounted for. So I just get the feeling that it's not as easy. I don't know. In theory. Okay. Maybe I'm just being paranoid then. Alright, so 7.81 squared times 2.13 minus 34.6. Over 41.748. Where does that put us? Alright, so H2 final height is going to be 2.28326 meters. Realistically, right? 2.3 meters. Given the other levels of precision, no, that's actually going to be one more. Given the other levels of precision, it's probably 2.28 meters. Not necessarily. So the way it's going to go here is that we've got our r squared system is going to be 4a plus 4b plus 4c is equal to 0. So a plus b plus c equals 0. Okay, the r system, I'm just double checking. It's probably unnecessary for me to actually do this. It's going to be 10a plus 8b plus 6c is equal to 0. Common factor is 2, so that's going to be 5a plus 4b plus 3c equals 0. And then the constant is going to be 6a plus 3b plus 2c is equal to 1. So, honestly, I just did linear algebra here. 1, 1, 1 augmented with 0. 5, 4, 3 augmented with 0. And 6, 3, 2 augmented with 1. And I don't know where my other TI calculator is. Let's see if we can struggle through this one together. Woo! Matrices. Nope. So if we subtract this from the bottom row, yeah. Let's see. It's gonna be R2 minus 5R1. Store back to row 2. Row 3 minus row 2 minus row 1. Do something slightly more exotic. Put back into row 3. So that's going to get us here 1, 1, 1, augment 0. Next, row 2 minus 5 row 1 is going to get us 0. This minus 5 of those is going to get us negative 1. This minus 5 of those is going to get us negative 2. And 0. Alright, take this and subtract the other 2. So that's going to get us 0. Take this, subtract, and subtract is going to get us minus 2, negative 2. Take this, subtract the other 2 is going to get us negative 2 as well. Oh, good, they're different. And this minus each of those is going to be 1. I may disagree with some of that. I don't know. Let's see. I might have screwed up. Alright, so multiply by negative 1. Multiply by negative 1/2. Nah, let's just add. So this is going to be row 3 minus 2 row 2. Go back to row 3. It's going to be 0, 1, 2, 0. So row 3 minus twice this is going to be 0. This minus twice that is going to be positive 2. This minus twice that is 1. Oh no, we're good. Okay. Here, I thought that was going to come back with a completely different value. Hello? Alright, there we go. Alright, so I'll multiply by a half. Row 2 minus row 3. Start back to row 2. Row 1. Skip. Zero, 1, 0, negative 1. Right? Because we're subtracting row 3. That's going to get us 0. That's going to get us negative 1. Oh, no. Okay. I think that was fine. And 0, 0, 1, a half. So yeah, now it's going to be row 1 minus row 2 minus row 3. Put back to row 1. So this is going to be our linearized, not linearized, row reduced echelon form matrix. So we get negative 1 here, a 1/2 here. Alright, so we subtract this, we get a positive 1. We subtract this, we get a positive half. Alright, so yeah, looks like whatever you had from before is good. Half, a half, negative 1. Limit as n goes to infinity. Sum r goes from 0 to n. Oops. So a half. To r plus 1. Okay. Give me 1 minute here. I will be right back. Alrighty. So half of that one. Plus, yeah, half of the last one. And minus one in the middle one. Alright, I think I'm going to need some convincing that this is going to actually telescope properly. So let's try it. So if R is 0, this is going to go in, and that's going to make a 1/2. Okay, minus. Got the right answer instantly. Interesting. Here that's 0, that's going to be minus 1/2. Okay, fair enough. And this one's going to be a 0 here, that's plus a 1/6. Right, so those are gone. 2, oops, that's in the 0 row, not the 1 row. So with a 1 here, that's going to be 3. It's going to be 1/6. Minus. With a 1 in here, that's going to be 1/4. This is going to be 5 times 2 is 10. Hey, Ivan. My day has been going pretty well. I had a very lively discussion with my pre-calculus classes today. So this new method that I've been working on is actually going pretty well. So this is Peter Liljedahl's building thinking classrooms in mathematics. I went to the American Mathematical Association of Two-Year Colleges, or AMATIC, national conference 2 weeks ago now. So the week before Thanksgiving. And it was amazing. Like, if y'all can go to professional conferences and get somebody to pay for it, just definitely do that. So Peter Liljedahl was a canoeist, an Olympic canoeist in Barcelona in 1992. Renegade? Oh, Outer Wilds. Yes. Sorry, it took me a second. Thank you very much. Yep, Outer Wilds is one of my favorite games, so I will often stop by Outer Wilds streamers, just for fun if I, you know, feel like having a mood. Yeah, no problem. And thanks for stopping in. If you ever have any math questions, Tuesday nights right here. Okay, so let's see. With a 2 plugged in, this is going to get 4 plus 1 is 5 times 2 is going to be 1/10. Minus 2 plugged in is going to get us a 4 plus 2 is 6. Okay, so that one can get rid of that one. And plus 2, 4 plus 3 is going to be 7. Ugh. Over 14. Oh, that's going to be gross. 3 in here is going to be 6 plus 1 is 7 times. Oh, no, okay. Okay, minus 3 times 2 is 6 plus 2 is 8. This is not going to be nice. 6 plus 3 is 9 times 2 is 18. 4 times 2 is 8 plus 1 is 9. So that's 1/18. Minus 8, 10. That one is going to drop out there. Plus 4 is going to be 8 plus 3 is 11. 1/22. I'm going to remain slightly unconvinced that this is a telescoping series. Because we're not getting stuff to drop out nicely. It's possible. Philly. Apologies. You can help me out with that one if you want. Yes. Area enclosed by polar curves is going to be a fun one. Okay, wait, no, sorry. Not all the things telescope in the first place. Okay, no, that's fine, that's fine. Okay, I see where I went wrong there. Okay. One more, just in case. 5 is going to make this 10, 11, 22. Minus 5, 10, 12. Plus 10, 13, 26. Okay. So, the 1/6 and the 1/12 are going to partially cancel. the 1/4 and 1/8 are going to reinforce. The 1/14, 1/18, and 1/22 are all going to reinforce. Seriously. Presumably 1/26 is also going to do it on this next row. So 6 should get us 12, 13 times 2 is 26 at the bottom. Yep. Okay. Okay. So that's going to get us 1/6. No, 1/12. Jeez. This is going to get us negative 3/8. This plus 1/10 is still stuck in there. This is going to get us 1/7. 1/9, 1/11, 1/13. Okay, all those odds are represented, but then we've got this other stuff, junk in here. Ay. So, Mr. I love BBQ chicken. I think that this may have something to do with the fact that the sums that they're trying to put together are infinite in extent, and it could be creating problems with trying to like combine things. I don't know why it should necessarily. But maybe I will I might be able to figure this out better later on. Yeah. I figured it might have been yours. Alright, two curves. I do not know what a Koopman operator is. Alright, so... So, Philae... Sorry. We've got here... is going to be some, not quite sector, but some sort of area that is going to be represented by these particular integrals. Sorry, these particular polar curves. Yeah, you just kind of made it up, right? Is that... Sorry. Okay, so for... if we let this be like you know, R1 and R2, then the way to figure out any one particular section of this curve would be to look at get one particular area like this. And again, here, we're going to assume that this is also going to be just a... really? That's awful. Oh. Okay. Changed it anyway. So one particular area like this. And so this here ends up being essentially what we call a D area. And the D area is going to be created by looking at the area of a sector. That's going to be created by our two angles here. And our two radii. Alright, so if we go with polar integration, it's not even there. That's terrible. Okay. Well, it is in my Calc 2 book, so we'll just pop this up here. All right, so typically a sector, area of just a sector like this, really, it's going to be equal to some theta that's not it. No, okay, that works. 1/2 theta times r squared, right? Just for a sector. But then we want to say, well, if we can do this for every single area within this thing, then we're going to be looking at individual sectors, a sub I, which are then going to be given by theta sub I and r sub I for each individual different sector. So like if we did this one over here, right, we can look at this, we can look at this, and assume that these are going to be circular sectors as well, and we want to shade in what's here. So again, in here, we're looking at A, no, not D, let's just do A sub I going to be given by 1/2 delta theta sub I times, now in this case, our boo. Yeah, okay. So we're going to be doing this in the same way that we do, how do you find the area of like a donut, right? How do you find the area of this thing here? So this is going to be area of the total minus area of the inside. All right, so we know what this inside area is going to be. We're just going to subtract that out from the total from the big circle. So here we're going to do the same thing. Here we want to say, okay, a sub I for R1 is going to be 1/2 delta theta times R1 squared. Then we're going to subtract off 1/2 delta theta sub I times R2 squared. But a whole bunch of that stuff is constants, so we can just factor it out. So this is going to be R1 squared minus R2 squared on the inside of the parentheses. You could also do it separately, because again, this is going to create right, and then that's also sub I for each of these, because anyway. Okay, so each of the sectors ends up giving us these little bits here. So if we wanted to do this between R equals sine theta and 3 cosine theta plus 1. Okay, so what we'd want to do is start looking for where these things are going to intersect each other. That's going to be really nasty. Yep. So maybe we'll do this as sine instead. Well, let's see what happens. So we go with Desmos. Okay, so we get R equals sine theta, and R equals 3 sine theta plus 1. So we ought to define what we mean by between these curves, because there are two different ways that it can happen. Typically when we do it this way, it's going to be between I think usually we state the outer curve first. I wonder what that would have been with cosine instead. It's no better. Actually, you know what? That is actually better. It's not going to be nice, but the values are going to be okay. So if we do it with a cosine, right, this is going to get us this cardioid shape. And then a circle goes up from here, goes up like that, and back there. Oh, cool. I'm glad you're not seeing this. Looks awful. Alright, there we go. So let's switch back to the other one. Okay. Yeah, so you're going to set them equal to find their intersection points. So here, and here, and here are going to be found. It's pretty obvious that this one is r equals 0. Right, so I can't even make it an ordered pair, really. It's just r equals 0. Now here's the other thing. The angles don't need to be the same. That's going to be fun. I mean, okay. So, no, okay, never mind. Their angles are literally the same. Never mind. Because otherwise they would be in the same location, literal location. Right, so from 0, we have this particular angle here. And this particular angle here, which is not 90 degrees. I don't think it is. No, it is, actually. Never mind. So r comma theta is going to be 1 comma 90 degrees. I shouldn't do degrees. Pi over 2. Yeah, with the angles, I thought for some reason that like one would fill out faster or slower than the other if the Yep. I thought one of them would fill out faster or slower if the frequency was different for one of them, but that's not true. So they fold back to the same place. Okay. So it's going to be sine of theta is equal to 3 cosine theta plus 1. This is going to be a little gross, but it'll still work. If we do sine squared theta equals 9 cosine squared theta plus 6 cosine theta plus 1. This can be traded. So 1 minus cosine squared theta is equal to that stuff. This is going to add a cosine squared theta to both sides. And subtract 1. Oh, nice. So that 1 goes away. And we got 0 is equal to, this is 10 cosine squared theta plus 6 cosine theta. That's pretty nice. So this is going to be 2 cosine theta times the quantity, 5 cosine theta plus 3 equals 0. So this is where the cosine of theta equals 0, where we've already got that. This is theta is equal to, on the first rotation, pi over 2 and 3 pi over 2. This could be plus or minus, and just plus. It's fine. Plus 2 pi times k, where k is an integer. Alright, or cosine theta is a negative 3/5. So theta is going to be inverse cosine of negative 3/5, or 2 pi minus that. I get you. All right, and again, plus 2 pi k. So with these, we're making a 3, 4, 5 triangle in either the second or third quadrants. With these two, we already had this here at 90 or pi over 2 and at 0. Do you mean the work that's being done by the incline itself? Or the work to get up an incline? Yes. So my guess would be that if I wanted to say, find the area between the curves, most likely I'd be looking for this one right here. Now, realistically, I would, if I were the one giving an exam on something like this, or like setting up a homework problem or whatever, I would probably zoom in and then like show only this segment and let my students fight it out over like what the actual value for this is, because that's always fun. But like I said, this creates a 3, 4, 5 triangle. The cosine is the short side, so that's going to be 3, 4, and 5. Yeah, finding extrema. So this angle is specifically going to be the inverse cosine of negative 3/5. or its explementary twin, 2 pi minus that. Yes, I did just say explementary. Yeah, it's going to be a bit hard. The sine of theta is going to be 4/5. Okay. Cosine of theta is going to be negative 3/5. Times 3 is going to be negative 9/5. Plus 1 is going to be negative 4/5. So it has to be negative. See, that's why you should know tensor calculus. No. Just no. You keep saying this. Alright, where is that also? So this is also theta equals pi. So I think if we take this as theta starts at pi and then goes up to the inverse cosine of negative 3/5, I think that'd do it. Well, where's pi though? Because this is this one. Pi is going to make cosine negative 1. No, because that's going to get us all this stuff way out here. Awful. probably pray. Uh, seriously though, what's going to happen, like almost guaranteed, is that this is going to be one of your limits of integration. And you don't have to plug it in right away. So let it be A, something like that. And then when you get this plugged into your, like when you want to plug it into the integral, it's almost certainly going to be either a simple sine or cosine. If it's the cosine of this thing, then it's negative 3/5. If it's the sine of this thing, then it's going to be negative 4/5. So I get you. You know, the good news about this particular thing being kind of ugly in that it's, you know, the inverse cosine of something is still that the somethings on the inside here and the inside of this argument are integers. So, I mean, it's a fraction, but it's a fraction with integers. The sides of the triangle are integers, like all the way through, all three of them. That's the problem. It's not supposed to be easy. It's supposed to get you to think. Well, you're not there yet. You got to build up to it. And don't work like super harder. Work smarter. Figure out how to break down all of these things. Yeah, it's true. And not to say you're doing it, but like the number one thing that people just need to do in order to like stop or really focus and pay attention and stuff like that is ditch the phone during class. Again, not to say you're doing it, but a lot of people just like... I had one student get overwhelmed today. He just kind of like sat down and played with his phone. I'm like, you need to like seriously talk with your fellow students here and get an understanding of what's going on. He was just checked out. I'm like, shh, that's not going to bode well. He was like, I did so horribly on my second exam. I'm like, I wonder why. So this is one of the reasons that I went with this and started like breaking the class and saying, you know, everybody needs to be standing, everybody needs to have a marker, and everybody needs to be writing and discussing with their group. Go. Yeah. Well, I mean, you know, trig is also a little bit weird, and if you learned it in a different language, it's completely, you know, messed up and wrong in English. I have a student who came from Venezuela, I think he said he was, and, like, he can do the math just fine. The problem is that his English translation of the math concepts he knows is just not there. Good news is he's still doing like reasonably well. He was coming to me today and he was like, I'm doing so horribly, I need help. I'm getting like a C. I'm like, the fact that you're getting a C in my class is like, not him particularly, but like the fact that anyone is getting a C in my class is sometimes a miracle. End of the semester, I usually make corrections. Like, oh, you've been working real hard. No, blame that. I hope you still come around and play with some math, regardless of whether or not you're done. Alright, let's see. Where are we? Let's switch mode here. Graph in polar. Nope, not X. Sine theta. There it is. Three cosine theta plus 1. Oh, whoops. There we go. Okay, so I got it. It's this one. All right, 2 pi minus cosine inverse of negative 3/5 is going to be the one that is here. And then as it keeps going, it hits this value. So our theta 1 for the limaçon is going to be this thing, 2 pi minus inverse cosine of negative 3/5. Then our theta 2 here is when r equals 0, and it's after that particular amount. Okay, so the value itself, nope, it's pretty close to 4.4. That gets it to be a little weird. Just because, like, we can draw like a secant between these lines, and then we can delineate both of these shapes. It's a little messed up. All right, cool. All right. So the actual value here is when 0 is equal to 3 cosine theta plus 1. So cosine theta is going to be negative 1/3. Theta is going to be inverse cosine of negative 1/3, or 2 pi minus that. We already know that needs to be in the third quadrant, I guess. So 2 pi minus inverse cosine of negative 1/3 is 4.37 something. Okay. So this is going to be a little gross, but it's alright. This is going to end up being. So here's the thing. This is not between the curves because I screwed up, like, my picture, essentially. Because it intersects at 0, we're not going to end up having anywhere that's between the curves. We could have done, for instance, on the circle here, and then down to here on the limaçon. Could have done that. Didn't think about it. So instead, what we're going to do is look at the two segments we do have. So we're going to go from 2 pi minus cosine inverse of negative 3/5 to 2 pi minus inverse cosine negative 1/3. What just happened? There we go. All right, and this is of the Limassol curve. 3 cosine theta plus 1 d theta. Then we need to add the circle. So the circle is going to go from 0 to, in fact, we could use practically any of them. Okay, so we can go from pi to 2 pi minus inverse cosine of negative 3/5. of sin theta, d theta. Oy. All right. So that's how to set it up. I'm going to encourage everybody to try that one out on your own if you know calculus. In all seriousness, right? This is going to be a negative cosine of theta. Then it's going to be evaluated between pi and 2 pi minus inverse cosine negative 3/5. Yep. So we're dealing with it as a sector. And these areas of sectors. So partial dz dx is taking your z, which is usually the objective function or temperature or density or whatever you're doing, and it's saying what is the change in that particular measurement, whatever it's going to be, in the x direction only. Yep, no problem. Good luck. All right, so Probably going to wrap up with the last few things here. And then we're going to be heading out because, see if I actually go to sleep after this. We'll see. But at any rate, I will be here on Tuesdays for math, and Friday nights we usually do game night, hang out, talk. Um, Occasionally people will ask questions on math. Lately we've been playing Astroneer. I kind of dragged my feet last stream because I was like, got all this like stuff to make in Astroneer, and I should have just done it because it would have been quick. But honestly, I was just not feeling it. Trying to figure out what I needed to do to get what where. It worked out okay, but at any rate, we are on Atrox and just about to go down into the planet. Do some core sliding to get to the center of the planet, and then activate the beacon that's there. Anybody who's never played Astroneer before, I highly recommend it. I usually recommend keyboard and mouse, but some people actually do like using controllers. All right. So, let's see who's live. We got Stevie. Oops. We got Boss Lady doing threat assessment on Elite Dangerous. So there is a massive update that just came out, and oh dear, some weird things are happening. Lexi is doing Valheim. Just tamed a wolf. Very nice. Domestic Dan is doing Undertale. Alright, let's go say hi to Boss Lady. Go see how crazy things are doing right now in Elite Dangerous. So I hope that everybody has a good night, and I will see you, well, hopefully for Friday for game night, and if not, next Tuesday for math stuff. And good luck out there. Stay safe. This is Obi-Wan Pez for Simplex Pachinko. Have a good night.